So here's the result of that. It's actually looking very fuzzy. This is kind of what I was trying to talk about before. It's very torn up by this disturbance. We could simply turn down how much disturbance there is, the strength. It was 25 and we reduced it to 10. But the problem is it actually looks quite good in the beginning. I wanted that strength to get us here quickly. I wanted it to tear up these features, and it's still pretty blobby and interesting structure here. It's just that by the end, it's just fuzzy and crazy. It's like a furry animal. We need to be able to basically tell the disturbance nodes to only work sometimes, only work in areas that we're interested in. In particular, I'm interested in it working in areas that are fast moving. And we've talked about this before, I believe. Now the rotation is pretty good at that, rotational force, where again, it's not adding any force, it's not adding any energy into the system, but it is still just rotating things around. Like even here towards the end, it's still making things turn and move in ways that are probably not really necessary. And certainly with the continuous, which is adding energy into the system or again, changing stuff around, yeah, it's too much. You can see it's just equally shredded everywhere. There's no interesting structure where some areas are more clearly ripped up than others. So all that is to say, we can hit pretty much all those points, especially the main one, which is be powerful at the beginning and then drop off as it goes, by using the speed of any given voxel to determine how much of this strength is going to be applied. So there's a few ways to do that. First way is kind of the most straightforward and visually interesting way. And then we'll do the more hardcore way. So let's go into the DOP network here on the left. I want to see it here. Now these nodes have a thing called control field. That's literally what we want. We want to have some field, have values in it that we say, well, when you're going slower than this, don't apply the strength. And when you're going faster than this, apply it. The problem is that we can't just put vel in here. This needs a scalar field. It needs it to be values, like the density field or temperature field or whatever. The velocity field are vectors that are directions in addition to being speeds. So there's just not a way to say the velocity from 0 to 1 when the velocities are like 5, 6, 2. Like this doesn't translate. So we need to extract the speed. We need the magnitude, aka the length of the velocity vectors. So to do that, again, the most straightforward way of doing it is to literally make a speed field that we can then put in here. So I'll put speed in here for now, even though it doesn't exist yet. But let's make it. Let's do a gas match field. Gas match field will make a new field. And again, a field is any of these things in here. These are fields. Oh, let me turn off. What is that we're seeing? Oh, that's the visualization from this. So I will turn back on density here just so we have something that we can see. Very good. So gas match field. Let's make that speed field that we've promised ourselves we'd one day own. Reference field doesn't mean that we're copying this field, but it does mean it should have the same size and number of voxels. The voxels should be the same size and such. And so rank is scalar. So we can use a vector field as a reference field, but this one's going to be scalar. Okay. So now what should go into that field? Use a gas analysis. We'll analyze the velocity, and we'll put it in. So the destination is speed again. Source again is velocity. The analysis can be length. And that's pretty much it. I'm going to plug that in here. We need this to exist before we get to these nodes, so make sure it happens first. So I click these little up arrows to get gas analysis to be first in line, which you can see by it being the leftmost input here. So now we have that field. If I press play and a middle click and hold somewhere, I'll see speed is there. Let's say I wanted to see it. I could do a scalar field visualization. Put that here at the top. Say show guide geometry, say, use plane. And there we can see it. And as you might imagine, these are the tiles and things, but the ones that are nearest to the smoke are the only ones that matter anyway. So you can kind of you can remap these things to kind of find where we're trying to target. So I could do like something like this. So what we're essentially saying is apply it where it's in these red areas and taper off out here. Or more importantly, taper it off just as the sim goes on, because the sim is going to slow down in general. So that's what we're targeting. Speeds between 1 and 3 and beyond 3 really. But certainly below 1, don't apply any of this disturbance. So that's our field. We can turn this back off. Or we can just turn it off on this, either way. So we have it now. So under control, speed, let's do the same ones we just came up with, 1 to 3. And let's just copy that over to our control here. Speed, 1 to 3. And let's see what that looks like. And before we continue, I'm actually going to give us a little bit more resolution also, 0.08. And that'll hopefully let us see these little details that we're talking about a little bit better. And let me make sure I want to keep this, so turn that off to ensure that we can keep that. And let's see what we get. And this is the result of that, and it is much, much better. Much, much, much better. So we're still getting the same breakup early on, as you can see, but now it's allowed to kind of come to a rest where we have more broken up areas still here, but we only have bigger features like here and here. It's just a more interesting array. And in general, it just doesn't end up looking like a mess. I mean, again, this is what it ended up looking like before. It was like a poodle. This ultimately reaches a fairly similar overall shape, more or less, but it's just much more interesting. So that's the key to speed-based disturbance, or speed-based lots of things, honestly. Yeah, I recommend it. I've been advocating for this since the first version of this lesson like 4 years ago, and I'll continue to do so. And so does everybody else. So do it. You do it too. Now, okay, we did it the straightforward way, though. I promise you there was a more complicated way. It's not actually that bad, though. The problem with doing it this way, such as it is that we have a whole other field. Is that a huge deal when the simulation already has 1, 2, 3, 4, 5, 6, 7, 8 7 other fields rather? No, but it does take memory. The speed thing, never mind the actual computation of the length, because we'll have to do that either way. But it does just take up memory. We have an entire 2.2 million voxels that are being spent on this. We don't really need to do that. We can just calculate it on the fly. But in order to do that, we need to crack these open. So let's just do with one of them. All this really could be avoided if, side effects could pretty easily build this into this node. I guess somebody really should just submit a feature request here where we can just put on this thing determine the length of the incoming vector field or whatever. But anyway, we can do it ourselves. So I just right-clicked on this and I said allow editing of contents. There, allowing editing of contents. And let's go in. Here we are. We have a bunch of stuff over here that says enable CL, first of all. Now that would be useful if you had OpenCL on. OpenCL is of course what the various parallelized hardware can use. Sometimes your CPU can use it. Usually it refers to your graphics card doing a thing. We can't really use it here because, when you make your sim be super high resolution, I shouldn't say you can't use it here, but by the time you end up making your sim super high res and it's taking up many gigabytes of RAM, it's probably not going to fit into your graphics card's RAM anymore. I have a pretty good graphics card and it's 11 gigs, but I have 128 gigs of RAM on my computer. So even if the graphics card would be faster at doing it, you know, your regular computer can ultimately just handle more, even if it's going to take some more time. So suffice to say, we're not going to be able to use this anyway. So we're going to target our efforts here on the non-OpenCL one. And this is just the visualization stuff here. So there it is, gas field VOP. On top, we actually say what field we want to use. So in our case, we want to use the vel field because we're not going to make the speed field anymore. Now this is called control field. If we go inside and we look at this, and we go to the data bindings rather, we can see, oh, here's that control field thing. Middle click on it and you can see it's what I typed. It's vel, because this is literally looking at that parameter. Vel is being remapped to something called control. So just know that when we're inside, it's not going to say control field, which is what the parameter was called. It's just going to be called control now. Not really sure why, but that's what it is. So this whole gray block down here is called control. It's all the control stuff. Here's that control parameter we were just talking about. I'm just going to pull it out here. Say this uses a vector now instead of a float, because that's what the vel field is. And that whole length thing that we did before, where we're just trying to find out how long the velocity vector is, because remember, velocity is a direction and a speed. The length will get us just the speed of that vector. And that's it. We're done. And now we don't have to devote an entire field to that. Now we won't be able to visualize it anymore, which is sad, but otherwise it's really pretty much exactly the same. We can go in here and do the same thing again, or we can just duplicate the other one. I guess to be safe, I'm going to duplicate this one, and I'll just call it continuous again. I don't remember what the full name was, but whatever. This was a continuous-based thing, not rotational. Control is vel, and the binding was the default density. So, but everything else obviously is the same. The only thing we really cared about was this. So that's it. So let's run it again and make sure that it looks pretty much the same. It might technically look slightly different, but it should be virtually identical. I'm not even really sure why it would look any different at all, but there's probably going to be some floating point rounding something that accumulates over 72 frames that makes it look slightly different or whatever. So this is what we had, and let's hope that the new one looks the same. So it's done, and yeah, it's pretty much the same. We can look at, let's say, the last frame, which would be the most telling, because that's where the greatest error or difference between the two would show up, and you can see it's pretty much identical. It's not identical, which is interesting. If you look at this feature right here in the middle, compare these two, it's not quite the same. But honestly, for it to even be this similar, like, it must have been pretty close. The more you look at it, the more you can see it is almost exactly the same. I don't really know why it's not exactly the same, but it's pretty close. Good enough. I'm gonna keep using this way. I'll keep this around, but I'm gonna keep going forward with this because honestly, I mean, it's better. What can I say? It uses less memory, and there's really no downsides to it otherwise, except for, you know, the visualization thing. So that's it for speed.